So we're going to change gears a little bit today. I'm going to start talking about some new things for us, but it's actually not so new. What we've been talking about in the last few lectures was iterative techniques for eigenvalue problems. What we talked about in that case was you take a matrix, you first sort of these leading eigenvalue methods, what they first do is they reshape that matrix by doing some bidiagonalization, for instance. That's one way to do that. That's what you do when you're going to do, like, for instance, compute an SVD. You do bidiagonalization first, then you iterate to make it diagonal from there. And so this idea of iteration entered in to our methodology and to our computational algorithms. So one part of it was just completely rule-based, reductive, like LU. There is no iteration. It's just you do a certain number of operations, there's your solution. Whereas here in the eigenvalues, you do a certain number of operations, then you switch it over to an iteration algorithm, which you want it to converge to the eigenvalues and eigenvectors. And so we're going to build on this theme and just come back to AX equal to B. So really what we're going to start doing is thinking about, well, that pin's done. Iteration methods. So iterative techniques for AX equal to B. So again, pretty much everything revolves around AX equal to B and decompositions of A, which again, the decomposition lets us solve AX equal to B, okay? Or lets us characterize A. So I want to start off with a simple example. And I'm going to just show you, we're going to start off by writing some code actually. So we're going to do a little bit of MATLAB today and just do a little bit of iterations to try to solve some very basic AX equal to B problems. So I'm going to start off here with a simple problem, which I'm going to write as follows. It's 3 by 3 system, 4x minus y plus z equals 7. 4x minus 8y plus z is equal to minus 21 minus 2x plus y plus 5z is equal to 15. Okay, so that's our system. 3 by 3 system of equation, and this is not that hard to solve, right? So in some sense, if you were going to solve it, you could do Gaussian elimination, LU decomposition, whatever you want to do. You could do this one by hand. You put it in as sort of the, whatever. Gaussian elimination is a very simple way to do this one. But I'm going to change the way we do this now. What I'm going to do is something interesting. Well, I mean, interesting is a relative term, but let's just play along as if this is really interesting what I do next. What I'm going to do is say, okay, from the first equation, I'm going to solve for x. From the second equation, I'm going to solve for y. For the third equation, I'm going to solve for z. Okay? So what's going to happen here? From the first equation, solving for x, that means I move the y over and the z over. So I get a 7 plus y minus z. All right? And then I divide by 4. Now, of course, I don't know what y is, or z, or x. But here we go. I just rewrote that equation. And I think we'd all agree that that works. I'm going to do the same thing for the other two equations, but the second one, I'll solve for y. Now, if I solve for y, notice that I have a 21 over here. This is minus 8y, so I could make it plus 8y over here, move the 21 over, it becomes plus 21. So it's 21 plus 4x plus z, and all that's going to be divided by 8, which was in front of the y. Okay, I hope you're marveling at my algebraic skills. Hopefully I did it right. Okay, Now for the third one, let's solve for z, right? So I'm going to take this 2x over, the y over, and divide by 5. So I'm going to have 15. I'm going to move the x over here, the y over there, and I'm going to divide by 5. So really, to some extent, I've done nothing. I've just taken the governing equations, 3 coupled equations, here they are, right? Algebraic equations, and we're actually trying to solve for x, y, and z. And all I did is I just rewrote them in this way. So there's nothing I've really done at all. And now here's where it gets kind of interesting. What we're going to do is we are going to take these and make an iteration scheme out of them. So what it is, take this here, and here's what I'm going to do with the iteration. I'm going to give you some initial guess, a vector which has initial values of x, y, and z. And then what you're going to do is from those, I'm going to make an iteration scheme here, which is going to say my next value, x of m plus 1, was the old values. And that's how I get my new value. Y of n, then y of n plus 1 is equal to x of n there, z of n. And z of n plus 1 is equal to x of n, y of n. So all I did was said, if I give you, and then n equals 1, 2, 3, and so forth. I'm just going to put these in and iterate. Guess some values of x, y, and z. Throw them in here. And when I guess these values, I put them in here as x1, y1, z1. I get to x2, y2, z2. Put those in here to get to x3, y3, z3, and so forth, and just start iterating. And then the question is, what happens when you do that? So let's write a code to see what happens. So what I'm going to do with you is do a screen share, and we're going to do exactly that. We're going to just iterate on this set of formulas here to see what happens. So let me go ahead and do a screen share here, and we're going to do my whole desktop. There we go. Share. Okay. All right. And let's put this down. Okay. There we go. Hopefully you guys can all see my screen here. And we're going to just do a program. Clear all, close all, CLC. So that's always how I like to start my programs. So there we go. We cleared the whole slate. And now we're going to build this program, which basically does this iteration procedure here. Okay, so first of all, I have to guess some initial values. So let's keep track of this. There's a lot of different ways to do this, but let's just do, I have an x value initially, I don't know, guess 13. If you were in class, I'd make you guys guess what these numbers are. And I don't know, pi. Okay, there we go. Those are my guesses for x, y, and z. So I just start this off. And by the way, those are clearly not the solution. Actually, I haven't told you what the solution is, but those are not it. And I just say, I just give you some random values of x, y, z. You saw that I just guessed it here in person. And what we're going to do now is we're going to just basically say, okay, let's go through this. And let's go ahead and, in fact, I'm going to make these vectors because I want to keep track of them as we go along. As we iterate, I want to see what happens to these values. So the first value, x1, y2. And then now I'm going to say, do a loop for j equals 1 to, I don't know, let's do this loop 50 times. There it is. Sorry if the blue is a little bit light there, but that's what we're going to do. We're going to iterate 50 times doing this kind of structure here. And so what does it say? What it says here, then it says x of j plus 1 is equal to, and I have a formula up here, and the formula says I have 7 plus y sub j minus z sub j, and all that's divided by 4. Okay, so that is the expression I derived from the first equation. And when I moved everything over to the other side, I got this expression for x as a function of y and z, and there it is. So I'm just saying the next value of x is given by the previous values of y and z. All right, let's do the same thing for the y values. And the y values, I also had a formula up on the board. It's 21 plus 4xn plus z of n. So I'm going to put those in. And your job is to unmute yourself if you see that if I have a typo in something here. Okay? Okay. All right, there we go. And then finally, the z sub j is 15 plus 2 times xj minus y of j, all divided by 5. So there you go. That's my loop. I give you some initial guess. There they are. And I'm just going to throw it into this iteration scheme. And what I'm going to get out is just a series of numbers, which is x being updated from the previous values to the next value. Same thing for y and z. So we're going to do this loop. And then at the end of this loop, in fact, I'm going to only do this loop 30 times. I'm going to plot x in fact, through this iteration, since I'm going to go 30 times, I'm going to end up with 31 values, right? So from 1 to 31, I will plot x. From 1 to 31, I'll plot y. From 1 to 31, I'll plot z. So they'd be in different colors. We'll see what happens with them. And in fact, let's plot these with balls, because remember, it's a actually, just see what it plots on its normal thing. Okay, everybody go with this. This is just a simple little code, just an iteration procedure. There's a couple things that computers are really good at. One of them is iterating. In fact, that's probably one of the best things it's good at. You're right. That's what you normally use a computer for, is iterations like this, because it'll just do that without complaining. But you would probably complain if I made you do this loop 30 times in your head or write it down on a piece of paper. But not a computer. It'll just do it. Ready? Let's run it. See what we get. Oh, let's call this call this 584 demo. Demo 584. Save. It's running, done, and there are the values. And of course, you can't see it because default settings are. Actually, I want to do line width. Let's run it again. All right, there's a little bit better. Everybody see that? Right, so I have to wait till. Let's blow this up a little bit. Okay, so something interesting is happening here. So what you're seeing there is these 3 values of x, y, and z. And as I iterate, and what often happens in iterations, there's actually some very interesting things that happens in iterations. When you iterate things for a long time, one thing that can happen is the iteration can converge to some value, like it's doing here. Another thing that can happen is it can blow up. Another thing that can happen is when you iterate, you can get, some chaotic mess out of the back end. There's lots of things that can happen. But what's interesting here is notice it's actually converging to some values. And of course, if we want to know what those values are, I can just simply come here to my terminal and say, what's the last value of x? It's 2. What's the last value of y? 4. What's the last value of z? 3. So it's converging to 2, 4, and 3. By the way, I could also ask the following question. What if I were to solve this problem, ax equal to b? And in fact, let's go ahead and do it. The matrix A in the system I had written down on the board earlier was 4, -1, 1. That's the first row. Second row is 4, -8, 1. The third row is -2, 1, and 5. And b is equal to 7, -21, and 15. And so the solution to this is x is, or let's not call it x, let's call c is equal to a \b. And let's actually have it print out to the screen what these are. Remember, when this thing was iterating towards, it iterated towards x was 2, y was 4, z was 3. And when I just solve this, there's a solution. And check out what c is. 2, 4, and 3. So when I did this iteration procedure, the iteration solved ax equal to b for me. There was no deductive formulation here with LU decomposition, Gaussian elimination, or something like this. All I did was took that governing set of equations, solved for x, y, and z, and look what happened. It totally worked. I actually got the solution out just by doing iteration. Okay? So this is very interesting. This is starting to highlight something, a very different strategy for us computationally, which is instead of a progressive set of algorithms that reduces ax equal to b into some form where I can just solve for it, this is just simply, it seems to me, seems to you at this point maybe, that I just made up some iteration scheme, let it go, and the iteration itself produced this solution to this ax equal to b problem. So anyway, that's, I think, kind of remarkable. It's kind of an interesting property. And then the question is, we're going to start asking is, I wonder if this is, maybe we should start thinking about what this means for us in terms of solving problems, because we're actually going to spend this week talking about solving ax equal to b using iteration schemes. All right, so I'm going to stop sharing for a minute. We're going to come back to coding in a bit. All right, so hopefully that seemed like a little parlor trick, a little magic trick. Look at that. You just take this equation, you just write it in a different way, and you just set up an iteration scheme, and boom, it works. How did that happen? Let's try this trick again. Okay, ready? We're going to do it again. You guys all saw what I did here from these three equations. I solved for x, y, and z. There they were. Set up an iteration scheme. Just let that thing go. And the resulting values, in fact, it converged within, like, if you notice, I went 30 iterations, but pretty much it had been converging within like probably 10 iterations that got me the solution. Okay? So let's come back to this problem. And let's do one thing. I'm going to take this again, and we're going to work on it. And what we're going to do is we're going to rewrite these equations. Specifically, I'm going to ask you the question, if I were to take this row and switch it with this row, you would agree, I think, that, well, I didn't do anything, right? I just switched two rows. They're still the same governing equations, the same 3x3 system of equations, right? So I just switched them. So in other words, I could write this as negative 2x plus y plus 5z equals 15, 4x minus 8y plus z equals negative 21, and then here, 4x minus y plus z is equal to 7. In fact, when we did the LU decomposition or Gauss elimination, remember that we always had to keep track of whether we were going to switch rows, right? Because we know we can just switch rows. They're the same governing equation, so switching rows, all you were trying to do is avoid a zero pivot. And so you could do that by switching rows. And so I did switch rows. They're the same governing equation, same solution, 4, 3, 2, right? Which is we had on the computer there. All right, but let's try this trick again now. From the first equation, solve for x. From the second equation, solve for y. From the third equation, solve for z, then make an iteration scheme. Okay, so from the first equation now, I'm solving for x. So this is minus 2x. So I'm going to take the minus 2x over here. It'll be plus 2x, bring the 15 over. So it's going to be minus 15 plus y plus 5z all divided by 2. Okay? So the minus 15, that comes over as 2x divided by 2. That's what you get. from the second equation, I get exactly what I had before. So I should have just not erased it and kept it, but fine. Y is equal to, so I moved the 8y over here, the 21 over there. So I have 21 minus 4x plus z. Sorry, I brought that over here, so it's plus 4x. All right, so 4x z, the 21 comes 8 comes over here. So there's a divide by 8. Finally, from the third one, z was equal to, I can just move everything over. You have 7 minus 4x plus y. Everybody agree that I mean, look, all we did from here, I solved for x, y, z. I just changed rows. From here, I solved for x, y, z. I get a different iteration scheme now, notice, because now I have x of n plus 1 is equal to this equation. Y of n plus 1 is exactly what I had before, and z of n plus 1 is this here. Okay, so a slightly different iteration scheme. Same set of equations. So really, same solution, just interchanged rows, different iteration scheme, but let's go to it. Let's go try to do this because it should work, right? You should get the same solution as before because, of course, the solution didn't change. It's still 4, 3, 4, 2, okay? So let's go ahead and set up an iteration scheme to do this. So I'm going to go back to screen share. Share the desktop, boom. There we go. I'm back here. So we're going to keep this, right? This is our method 1 for doing it. And we're going to start off with the same guess. Let's go ahead and start off with the same guess. But now what I'm going to do is let me just say that let's run 2 iteration schemes simultaneously. So like I'm going to make x2, 1 is equal to x1. So I'm going to, in other words, I'm going to have 2 solutions, x and x2, and y2, which is, and what I'm going to do is compare these. How do they look relative to each other? Because in fact, they're solving the same system of equations, but they have 2 different iteration schemes. So I'm going to start off, I have this loop that's going to solve for x, y, z, and I have another, I'm going to have the same loop and evaluate what's happening to x2, y2, and z2. Okay, but now what does x2, y2, z2 look like? Well, that's this new iteration scheme that I just wrote up on the board. So let's go ahead and program this in. So you see that x of n plus 1 is the minus 15 plus y of n z of n. So you're going to get here x of 2 j plus 1 is equal to, you have minus 15 plus y of 2j, right? Plus 5 times z sub j, z2 sub j. Okay, all divided by 2. And then you have y of 2, j plus 1, is equal to 21 plus 4 times x of n, 4 times x, that's what you get there, 4 times x2 now because we're working with that, plus z2 of j, all divided by 8. Now this equation is exactly what I had before. Okay, so nothing changed with that equation right there. Because I only switched the first and third row. And finally, z2, j plus 1, is equal to, what I have up there is 7 minus 4 times x2, j, plus y2, j. All right, let's put some semicolons in there so I don't have to see all the output. Hopefully everybody agrees that this should produce the equivalent solution as that. Hopefully that's the case. That's what we want to check, is like somehow that iteration, if you've never seen this before, hopefully you're like, oh my gosh, you can just do that and iterate and it gets the solution. That seems magical. Kind of pretty cool, right? And hopefully that's your thought. And if you've seen it before, then this is Well, whatever. Maybe it's a boring lecture for you, but that's okay. We're still going through this to see what these are. So now what I'm going to do, I'm going to make a new plot. So I have figure 1, which will be the plot of the original iteration. I'm going to make a new figure 2, which will be this plot here, which is going to be basically same thing, but now I'm going to plot 30 iterations of x2 versus y2 versus z2. So 2 figures, and I'm going to say just go and see what happens here. Like, I'm feeling lucky. This iteration.
Hey, Professor, I think you might have a typo on x2. I think it should be negative 15 plus y2j.
Oh, yeah, right here?
Yeah, is that?
Yes, thank you. Yes. Yes. Any other typos? Thank you. I always like to get the typos before I hit return. I mean, usually in MATLAB, I'm always like, it complains because I did something wrong, but every once in a while, you got on a hot streak where it always works every time you hit go. All right, thank you. All right, now I think we're ready to plot these. Hopefully everything's fixed. All right, so let's see what happens. Run. Oh, okay. So here's what happened before, and here's what's happening now. So you say, what's happening? And by the way, do you see this number right there? I don't know if you can see it. It says times 10 to the 15. So what's happening is, in fact, let's go through a smaller number of iterations. Let's just go through 15 iterations. Let's go through 10 iterations. Oop. What happened? Oh, I see. I have to change these now. If I only do 10 iterations, got to change these to 11 now. Okay, let's run it. And there you go. And by the way, it already says 10 to the 5. So what's happening, I told you earlier, like iterations can converge. Look at this. They do beautifully in the first one. Iterations can do things like diverge, go to plus or minus infinity. And in fact, that seems to be what's happening with these guys. Notice this number up here, 10 to the 5. So already you started with values that were reasonable, you know, whatever, order 1 values. And now they are 5 orders of magnitude bigger after only 10 iterations. In fact, they're going to infinity very quickly. What we know is the answer, this one converged to the answer, and this one did not. So, you know, the initial hope, you know, like say, hey, look at this, check out this magic trick I just did. And the magic trick I did was say, just take the governing equations, rewrite them, iterate. And it works. It got to the solution. I just iterated on that thing. It worked. But then I just did the same equations, did an iteration, and it blew up. So what's going on? How obviously you don't want to use a method that is liable to break like this, right? What you'd like to do when you solve equations is you want them to work consistently. Okay? So let's talk about the difference between these two sets of equations, and it's going to highlight a really important part of iterative schemes, which is having to do with the diagonal of a matrix. Okay, and the diagonal of a matrix, remember when we did power iterations with eigenvalues, remember how the largest eigenvalue would show up, or the eigenvalue closest to my parameter mu, which would be highlighted, and all the iterations, everything would go away to 0 except for one of these except for the largest one, which was due to the power iterations. And so what we're going to talk about here is what's the relationship between that and these techniques that we've developed here. Okay. This has everything to do with the matrix A in these two cases. We can agree that they're the same governing equations, same solution. But the way I've written this one, let me write it. What's the matrix A? The matrix A in this case is 4, -1, 1 from here. The matrix here is 4, -8, 1. And then here it's -2, 1, 5. And then the B is this here. But I'm just going to focus on the matrix A. When I look at this matrix, which is the same solution, all I've done is interchange rows, columns. All I'm going to do is switch this with this, first and third rows. So I'm going to get -2, 1, 5, 4, -8, 1, and then 4, -1, 1. Okay, same solution, but here's the big difference. I want to highlight it in here, which is when you have governing equations like this, and we're going to talk more about how these iteration schemes work, but the difference between these two formulations is what's called diagonal dominance. Okay, and in particular, the way you define whether a matrix is diagonally dominant is you look at, for each row is the absolute value of the diagonal, and you see, is it bigger than the sum of the rest of the terms? So what do I mean by that? I'm going to erase this, and let's look at what diagonal dominance means here. Is this matrix diagonally dominant, or what's called strictly diagonal dominant?
About the diagonal.
Is
the sum of the diagonal the same as the trace of the matrix?
The sum of the diagonals? Yes.
Okay, thank you.
Yeah. So what I want to look at is the diagonal term here is 4. Is 4, the absolute value of 4, which is 4, bigger than the sum of the absolute value of the other terms, which is 2? It is. Here's the diagonal. Is 8 bigger than sum of the other terms, the rest of the row? It's bigger than 5, it is. Is 5 bigger than the sum of the other two? Absolute value of the 2, 5 is bigger than 3. So this means it's strictly diagonal dominant. This diagonal dominant is really important because it's very much like when we iterate on eigenvalues, it just, as you do the power iterations, essentially, everything disappears except for the diagonal term, where this is what is converging along these directions. Okay, and like I said, we're going to spend more time talking about more sophisticated methods for this. And in fact, the method we used, we're going to come back to it in a minute, was just if we take the current value and update it, it's called a Jacobi iteration. Okay, so Jacobi iterations, if it's strictly diagonal dominant, there's a theorem which states that if you are strictly diagonal dominant, you converge. Guaranteed. Great. And strictly diagonal dominant means you are greater, not greater or equal to, greater than. Okay, that's an important point to make. Let's talk about this one here. What about this matrix? Same solution, right? I mean, we all agree. All I did was interchanged rows. I go grab the diagonal term. Is 2 bigger than the sum of the other two? 6. And it certainly is not. The second row is 8 bigger than sum of the other two columns? 5, it is. Finally, this diagonal is 1. Is that bigger than sum of the other two, absolute value of the 2? 5, it's not. So this is not strictly diagonal dominant. So what's interesting about, if you're not strictly diagonal dominant, you can't say it's going to diverge. You can't say anything. You can't say it's going to convert. Sometimes it doesn't have to be strictly, it's not strictly diagonal dominant, it still converges. Okay. This is only a guarantee of convergence if you don't satisfy strict diagonal dominance. You can't say anything about it. But generically, if you don't satisfy strict diagonal dominance, it just also means your solution might blow up, which is problematic, right? Because if you're trying to guarantee that I put this in and get a solution, this is going to be a problem for you. Okay? So strict diagonal dominance matters. And if you have it, if you iterate, you converge to the solution. If you don't have it, you could blow up. You could converge. You don't know. You can't say anything specific about it. Okay, so this is going to be this is an important observation for what comes next in the next 2 lectures, which is we're going to build on these themes of iteration techniques for solving Ax equal to b. And notice how fundamentally different this is than what we've been doing. Everything we've been doing in X equal to b is having a progressive way to just get to the solution. We can even say it within order n cubed operations, I am guaranteed to get to the solution because there is a series of operations. As long as that matrix isn't singular, I just perform these series of operations. Okay, they're deterministic. I get an answer. Here, I start with a guess. And by the way, this convergence guaranteed for any guess. We'll do it in a minute. We'll just play around with some guesses. It doesn't matter what you guess. If you have a really bad guess, it might take more iterations to get to the solution, but guaranteed to converge, right? For any guess. And a lot of these algorithms, what they guess is just say, oh, I'm going to solve X equal to B. I put it in this form. I don't know. Since I don't have anything else better to guess, I'll just guess that X is 0. So you start there and it iterates to the solution. Okay? Let's show it. I'm going to show it on this method. In fact, the iterations we did here, which is you take your current values to update them all, is called Jacobi iteration. And let's show you what happens when we change guesses. All right, so I'm going to share screen. Share, boom. All right, so we'll come back to here. And remember, I just picked these randomly, 13, -5 pi. I could also just pick here, which is like, if you don't have anything better to pick, you can, 0, 0, 0 is perfectly as good as any other guess. You run that. Again, this is the one that blows up. Okay, right here. And then here's the convergence to the solution. So again, I just showed you different guess still converges really quickly to those solutions, which are 4, 3, and 2. Okay. I'm going to show you one other thing we can do with this. And notice, so first of all, I want you to know something here. By around 6 or 7 guesses, it's converging, right? This one here, of course, just blows up. So let's just ignore it. So about 6 or 7 iterations and it converges. Pretty close. I want to do one other thing here. I want you to start to look at this algorithm. Notice something. When here's this algorithm, I started with an initial guess of X, Y, Z, and then I use those values to get me new values of X, Y, Z. Now, presumably, when I update these values, in fact, I'll stop sharing for a minute. So the idea is I give you a guess, and I use that guess to give me new values of X, Y, Z. But notice in this algorithm, I first say, let me update X. Then let me update Y, then update Z. That's called Jacobi iteration. I just take the previous values and I create updates for all of the values. There is a way to improve this, what's called Gauss-Seidel. And what Gauss-Seidel says, well, wait a minute. In the first step, you updated X. Why wait till the next round of iterations to use that X? In other words, if I already have this new value of X, I can use it immediately. I don't have to update all the values. I can use that value as soon as I get it in my current set of iterations. So what I'm going to do is show you an update to the code which takes from Jacobi iterations to Gauss-Seidel iterations, which improves your performance because presumably every time you iterate, you get closer. And so I'm just using a better value faster. So let me just show you where this would change in the code. So here we are. Here's the code. So what I'm talking about specifically is, look, right here in this first line, I just improved my value of X, presumably, right? I took X of, I grabbed the Y's and the Z's and I got a new value, X of J plus 1. X of J plus 1 should be better than X of J. my second line of the code, y of j plus 1 is equal to, look at it, there's an x of j in there. But why would I use my old value of x of j when I have a new value of x of j plus 1? So in fact, right here, I can immediately use x of j plus 1. So I'm using my update as soon as I get it. So I take the x of j, I already have x of j plus 1, so use it immediately, specifically on that next line. And then I say, y is z of j plus 1. Notice it requires x of j and y of j, but I just have improved values of both of these. So I can put in here plus 1, plus 1. And now the idea is that I should get a better value of z of j plus 1 because I've already used better values of x and y. Was there a question, by the way? Someone? No? Okay. So this is called Gauss-Seidel iterations. Remember that when we do this coding, it's not just about getting the right answer. It's about how fast can you get that answer and how accurately. So in this case, Gauss-Seidel, you trade this out, not because, hey, look, I got a better answer than Jacobi. You get the same answer, it's just that you might be able to get it faster. Remember, computations is all about this combination of accuracy and speed. And so this is getting at the issue of speed. How can I use my results on the fly to get this faster? So let's go ahead and run this. And let's go dump this out. And I want to show you this. If you remember in the last plot, I showed you it took to about iteration 6 or 7 to get this to converge. But this thing here is already starting to converge towards that around iteration 4. So 3 or 4 iterations. In fact, you know, a lot of times if you just look at this quantitatively, you know, I've done this before where you can just take this simple system and just say, at what point do they reach about the same error? And usually this Gauss-Seidel often goes about twice as fast as Jacobi iterations. So this is the idea, is that you just say, hey, look, use your knowledge on the fly as you're building these models. And then that's going to converge faster to the solution. And I just showed you that, okay, on this very simple example. So this is kind of interesting, right? Setting up these architectures. And I want to just highlight one key aspect of where this stuff is actually used in practice. A lot of scientific computing revolves around solving high-dimensional, big-scale problems. A lot of those high-dimensional systems, the matrices that you're generating actually tend to turn out to be matrices generated from differentiation matrices. So, for instance, let me just draw you something. If you were to take a vector, u, and let's say take 2 derivatives of it, then if I discretize this, the 2 derivatives, the second derivative formula, and I'm not going to go into details here, but it looks like something like this. If I'm at the nth point, it's basically point front minus twice this point plus point behind over delta x squared. This is an approximation to the second derivative using just your slope formulas, essentially. But what does this look like in terms of a matrix? Well, in terms of a matrix, a second derivative matrix looks something like this. It's 1 over delta x squared, negative 2 down the diagonals, and 1 on the off diagonals. 0 everywhere else. And these kind of matrices show up everywhere because they're coming from physics and coming from engineering problems where you say, I'm going to solve this problem, so I have this massive matrix, but notice the structure. In fact, it's almost all zeros, and it's got this tridiagonal form. And remember what we tried to do when we solved these for the eigenvalue problem? Step 1, try to reduce your matrix to like tridiagonal form, or in the case of the SVD, bidiagonal form. Step 2, iterate to the solution. I've already got this thing as a differentiation matrix. intra-diagonal form. And then you ask, okay, good, I could start, maybe I could do iterations. Notice the following. Is this strictly diagonal dominant? The diagonal is 2, the absolute value. The off diagonals, there's 1 on either side, is 2. Is right at the edge. It's an edge case, right? You're right at, you're not, it's instead of being greater than, if it was greater than or equal to, you'd be fine, but this is exactly equal to. The diagonal is exactly equal to the off diagonals, right? So you can't say there's a guarantee of convergence, and we'll talk about that. But this is how these matrices show up. This is why iteration matrices are so prominently used in very large scale computations, because the matrices that show up often have this form, and people, state of the art is to use not some kind of LU decomposition or these different ways to solve matrices, but they actually use iterations to solve for these large scale problems. That is the sort of state of the art, fastest way to do these things. Okay, and we're going to talk about 2 methods in particular: by conjugate gradient descent method and generalized method of residuals in the next 2 lectures, which are sort of these high-end, methods for solving large-scale computation problems that are of the form AX equals B by taking, explicitly doing iterations in a smart way. All right, that's where we end.